Hey everybody, in this video I will do a Falcon LLM fine-tuning on Open Assistant Guanaco dataset. So initially all the regular imports, so here the transformer relevant modules, auto model for causal LM, auto tokenizer, bits and bytes config because I'll be using QLORA, and then the PEFT module. So I need the LoRA layer from the PEFT module, and for the actual training, I'll be using the TRL library because nowadays almost all of the LLMs are being trained using these TRL library. It's a hugely useful one. And then I just need to define a couple of classes for defining all the configurations for the training. So the first class I'm defining is this one, model arguments. And here you will see many of the configurations that will be needed actually while applying the bits and bytes config. So I will talk about those individual parameters in detail when in a second when I explain the bits and bytes configuration parameters. But for now, you can see that all I'm doing is just simply defining, for example, use nested quant equal to, that's a field, default, false, and metadata, which actually gives you some help or some notes on what this is about. So this is activating nested quantization for 4-bit base models. And the same structure I'm following for the other configuration parameters as well. And yeah, the next one, my class is script arguments. And the very first argument within my script argument class is this one, local rank. So this is about the rank of the process during distributed training. So in the context of distributed training, a single training job is split across multiple processes, often spread across multiple machines or nodes and multiple GPUs. Each process running a piece of the training task is assigned a unique rank to identify it. The local rank is specifically the rank of a process within a single node. Imagine you have two nodes, each with 4 GPUs, making it a total of 8 GPUs. The global rank would be an index from 0 to 7 to uniquely identify each process across both nodes. The local rank would be an index from 0 to 3 for each node to identify which GPU is being used for that node. So that means that when you initialize a training environment in a distributed setting, this local rank parameter helps the process know which GPU it should use on its local node. It effectively scopes the process to its designated GPU. This is crucial because each process needs to manage its own sub-batch of data and perform forward and backward propagation. Eventually, gradients or model parameters are synchronized across all processes, often in a reduce scatter fashion for optimization step. The use of local rank becomes particularly important in strategies like distributed data parallel (DDP) in PyTorch. DDP uses local rank to partition the mini batch across the multiple GPUs on a single node. And here you can see that I am selecting default as -1. That's normally used. So why default is -1? So when local rank is set to -1, it generally means that the training is not being run in a distributed environment. The framework would then default to using all available resources on the single machine you are running the training job on. This allows for flexibility, enabling the same code to be used for both single GPU and multi-GPU training setups without modification. And in the backend, libraries like NVIDIA's NCCL are often used for efficient multi-GPU communication. When a process is initialized, the local rank often gets passed as an argument to these libraries to establish correct communication channels. And then you have this parameter per device train batch size. So this is the batch size per GPU, XPU, TPU, or whatever the hardware that you are using. So if per device train batch size is set to 8 and you have just 1 GPU, that means your total effective batch size for the entire training is 8. And if for the same situation, if you have 4 GPUs, your total effective batch size for the entire training is 32 because there will be 8 per GPU. Similarly, for the per device eval batch size, this is a batch size for evaluation. And then I have these gradient accumulation step. So what is gradient accumulation during the LLM training? Gradient accumulation is a technique primarily used when the batch size required for training a deep learning model is too large to fit into the GPU memory. Instead of reducing the batch size, which might affect the training dynamics, for example, model might converge to different local minima with smaller batch sizes, gradient accumulation accumulates the gradients over multiple mini batches and updates the model weights less frequently. So the gradient is as you know, that it's a measure of how much the output of a function changes if you change the input a little bit. So in standard non-accumulated stochastic gradient descent for each mini batch, you have a forward pass, that is compute the predicted outputs given the inputs of the mini batch. Then you have to compute the loss, that is calculate how wrong the model's predictions are compared to the true value. Then you have the backward plus, that is compute the gradient of the loss with respect to model's parameters. And finally, update the model's weights using the computed gradients. Now, gradient accumulation technique modifies this process a little bit. So under this gradient accumulation technique, you have the forward pass for the first mini batch, then you compute the loss, then backward pass, that is compute the gradient of the loss with respect to model's parameters. But here is the key. Instead of immediately updating the model's weights, keep the gradients in memory and repeat the previous three steps, that is forward pass, compute the loss, backward pass, for gradient accumulation steps number of mini batches, adding the new gradients to the stored gradients from previous mini batches. And once all the gradient accumulation steps mini batches are processed, update the model weights using the accumulated gradients. The key advantage here is that gradient accumulation allows simulating a larger effective batch size without requiring the memory for that larger batch. For instance, if you can only fit a batch size of 8 samples on your GPU, but you want to simulate a batch size of 32, you can use gradient accumulation steps equal to 4. This means you'd process 4 mini batches of sizes 8, that is totaling 32 samples, which is a desired effective batch size that you want for your case, before performing a weight update. However, note that while gradient accumulation helps in memory constraints, it does not provide the exact same regularization or noise smoothing benefits as genuinely larger mini batches. This is because even though the gradients are accumulated over multiple steps, the noise in the gradients is still present, just averaged over a few steps. But still, in many practical situations, using gradient accumulation steps and this technique will ultimately benefit you when you are a GPU constrained, which will be the case in many large language models. Alright, after that one, the next parameter that I'm going to talk about is max grad norm. This one, this will take an optional float value and the default is 0.3. So, the story here is like this. That is, when backpropagation is performed, each parameter's gradient is computed. These gradients indicate how much the loss function will change if the parameters are adjusted by a small amount. In some cases, especially in recurrent neural network and deep networks, these gradients can become very large, leading to what is known as exploding gradients problem. And gradient clipping is a technique to prevent that. That is, gradient clipping will prevent gradients from becoming too large during the training of a neural network. So to do that, if we consider the gradients as vectors, the idea behind gradient clipping is to scale down the gradients if their L2 norm exceeds max grad norm. The idea of gradient clipping is very simple. If the gradients gets large, we rescale it to keep it small. And that rescaling factor is defined by max grad norm, which here represent the L2 norm, and the default value is 0.3. And then we have max sequence length. So you need to make sure to pass a correct value for this max sequence length, as a default value will be set to minimum between tokenizer.model max length or 1024. That is in case if you don't pass the correct value. So here I am passing it and keeping the default value at 512. And then notice that this entire class, that is a script argument class, there is a data class decorator before it. So this decorator takes care of automatically generating the init method, the REPR method, or underscore EQ method, and does quite a few other things for us. And it's pretty useful. You can just read about this. And hence we have included this decorator both for this one and also this one. And it's a very common practice during LLM training that most of your classes will have this decorator before the class definition. And some other parameters of this class, that is script arguments, these are bool. For example, FP16, BF16, these data types are all bool. It will take a true or false value, and we will see in a second that how I'm using them. And the rest of the parameters are pretty obvious if you just quickly read about them. So for example, LR scheduler type, default will take constant, else you can specify a value. You just need to go through the documentation for in the HuggingFace for these relevant parameters. And then max steps, warm up ratio, group by length, save steps, logging steps, etc. All right, so next method I'm defining is get model PEFT config tokenizer. This is where I'm implementing the BNB, that is bits and bytes config. And also I am getting, finally from this model, I'm just getting the model, returning the model, PEFT config, and the tokenizer. Let's quickly go through these individual parameters here of the bits and bytes config. So the first one, load in 4-bit. This parameter is for loading the model in 4 bits precision. This means that the weights and activations of the model are represented using 4 bits instead of the usual 32 bits. This can significantly reduce the memory footprint of the model. 4-bit precision models can use up to 16x less memory than full precision models and can be up to 2x faster than full precision models. However, if you need the highest possible accuracy, then you may want to use full precision models. And the next one is BNB 4-bit use double quant equal to true. This parameter enables double quantization, or also called nested quantization, which applies a second quantization after the initial one. It saves an additional 0.4 bits per parameter. And then the next one is BNB 4-bit quantype equal to NF4. This parameter specifies a type of 4-bit quantization to be used. In this case, NF4 refers to normalized float 4, which is the default quantization type. And the last one, BNB 4-bit compute D type equal to torch.float16. So this parameter determines a compute data type used during the computation. It specifies the use of the bfloat16 data type for faster training. The compute type can be chosen from options like float16, bfloat16, float32, etc. This configuration is needed because while 4-bit bits and bytes stores weights in 4 bits, the computation still happens in 16 or 32-bit. And here, any combination can be chosen by the user, that is by the developer. And the options are float16, bfloat16, and float32. And here I've chosen float16. And the matrix multiplication and training will be much faster if one uses a 16-bit compute D type. And the basic question you may ask is, does floating point 4-bit precision quantization needs any special hardware, or has it any hardware requirement? Note that this method is only compatible with GPUs, hence it is not possible to quantize models in 4-bit on a CPU. That's the only requirement. And among the GPUs, there should not be any hardware requirements about this method. Therefore, any GPU could be used to run 4-bit quantization as long as you have CUDA version equal to 11.2 or more installed. And keep also in mind that the computation is not done in 4-bit. The weights and activations are compressed to that format, and the computation is still kept in the desired or native D type. So within this method, I have this PEFT config defined because here I'm using the parameter efficient fine tuning, that is a PEFT, and also using LoRA, low rank adaptation. And for that, I need to define their relevant parameters. So the first one is this LoRA alpha. This parameter controls the scaling of the low rank approximation. It's like a balancing act between the original model and the low rank approximation. Higher values might make the approximation more influential in the fine-tuning process, affecting both performance and computational cost. And then I have these dropout, LoRA dropout. This is the probability that each neuron's output is set to 0 during training, used to prevent overfitting. So dropout is a general technique in deep learning to reduce overfitting by randomly selecting neurons to ignore with a dropout probability during training. The contribution of those selected neurons to the activation of downstream neurons is temporarily removed on the forward pass, and any weight update are not applied to the neurons on the backward pass. The default of LoRA dropout is 0. And then another important part of this configuration is target modules. So these are the names of modules LoRA is applied to. Here it is set to these few layers: query key value, dense H to 4H, dense 4H to H. So you will get the exact name of these layers by printing the entire model, whatever you are selecting. So in this case, we are using Falcon 7B, and when I printed the entire model architecture, these are the layers which are selected for my target modules. And in the same method, note this part of the code block, that is, it's an alert for bfloat16 acceleration support. So here, the storage.cuda.getDevice compatibility returns the major and minor CUDA compatibility of the current device. The compute, that is the CUDA compute compatibility, is a version number that corresponds to a specific GPU architecture's features. Here, the major version number of the compute capability is extracted and checked. For example, if the major is 7 and minor is 5, CUDA compatibility is 7.5. And here in this particular code, if the major version number is greater than or equal to 8, it indicates that the GPU supports bfloat16. This is because NVIDIA GPUs with a compute capability of 8 or higher, that is supporting the Ampere architecture and newer, include support for bfloat16 operations, which are designed to provide near float32 level of precision for deep learning. And this is a key line where I'm actually loading the model. So it's coming from my arguments, model name, and quantization config we have already defined at the top, which is BNB config, and device map 0 trust remote code is true. All right, so that's about this particular method, get model PEFT config tokenizer, that will return me the model PEFT config and tokenizer. The next another quick util method is parse arguments. So here I'm using these HF argument parser module of HuggingFace. So the HF argument parser class is provided in HuggingFace's transformer library, and this class takes one or more data classes and turns their data attributes into command line arguments of an argument parser object. And hence, that's what this is doing. Parse args into data classes. And then I have two more quick util method. This one is quite short, just a single line to load the dataset. And split, I'm only using the train portion of the dataset. And then get training args, and this is where all my script arguments will be used. So it is basically just returning the training arguments with all the parameters coming from the script args dot and then the respective parameter. So we have already discussed all these things during discussing these class script arguments. And then another util method, adjust model for BF16. So this method customizes the data types of specific layers in the model based on precision and performance trade-offs. The BF16 format can give speed benefits on hardware that supports it, but not every layer benefits or is even compatible with the reduced precision. Therefore, a selective application of bfloat16 or float32 ensures a good balance between performance and precision, and that's exactly the job of this particular method. So the function iterates over each named module or submodule within the model using named modules method. If a module is an instance of LoRA layer and the BF16 flag is true, the module's data type is converted to torch.bfloat16. And next, this part, that is if norm is name, norm in name module equal to module.to torch.float32. So the reason of doing this is that normalization layers such as layer norm are usually kept in float32 data type because lower precision like bfloat16 can reduce their effectiveness. This is due to the fine granularity of normalization operation, which can become imprecise in lower precision formats. And further, the last block here, that is LM head in name or MB tokens in name. So if the BF16 flag is true and these components are currently in float32, they are converted to bfloat16 to potentially benefit from the acceleration this data type can offer on certain hardware. And the rest of the code is pretty simple. So I'm getting my model args and script args from parse arguments. We have defined this method earlier. Then I'm getting my model PEFT config and tokenizer by executing this method get model PEFT tokenizer. And the dataset I am getting by load training dataset, which will load my dataset. And training arguments is just by what I'm getting by get training args. That is this method right here, get training args. All right, and then finally the trainer is I'm using SFT trainer. This is super popular coming from the TRL library. And it takes some standard parameters, model equal to model, train dataset is my dataset, and so on and so forth. Adjust, and then this thing you just have to do. We just discussed about adjust model for BF16 depending on various layers. So we are invoking that particular method, passing it the trainer, which I'm getting from here. And finally, the entire thing will run by running this line trainer.train. That will start the entire training process, and depending on your hardware configuration and the power of your GPU, it may take anywhere between 30 minutes to up to 3-4 hours for Falcon 7B. So that's pretty much ends this video, because like I said, this video I just did a code walkthrough of these Falcon 7B fine tuning on a particular dataset. So thank you very much for watching, and see you in the next one.